Hess's law and delta H reaction. That's what this is about. We've been talking about, heat transfer and things like that that deal with a lot of thermo stuff, but now we're going to deal with chemical reactions. So I want you to envision this reaction. In fact, I totally encourage you to take a picture of, or sorry, take a look at the picture that's in your book. This is known as the thermite reaction. On large scale, looks really cool, lots of energy given off, very exothermic reaction. Of course, this isn't balanced, so I could balance it. But it actually produces molten iron. That's how hot it gets. Very cool thing. You actually need to get it really hot to get it started. And so there's a picture there. So I encourage you to look at it. I'll show you a little mini thermite reaction in class. But ultimately, it's the kind of reaction where it's so hot that it can be challenging to find the heat of reaction. It literally is giving off so much energy. It's not like you throw a thermometer in the middle of some, flames and molten iron. That isn't what's going to happen. So we need a way to find delta H of the reaction on paper rather than having to do it via experiment. So the first thing we have to understand before we can do it on paper is something known as Hess's law, which I will just sort of kind of define for you right here. And Hess's law says that delta H of reaction will be the same whether the reaction takes place in one or many steps. And I think the best way to show that is I'm going to show that to you graphically. Most of you should have seen a graph that looks like this. It's a potential energy graph versus a reaction. And we can talk about the potential energy of the reactants. Sometimes you add a little activation energy and you can have the potential energy of the products. So like for this reaction that we're interested in, it's aluminum and iron oxide are the reactants. They contain a certain amount of energy. And the products are iron and aluminum oxide. They contain a certain amount of energy. And to get the reaction started, you have to add this amount of energy, which is known as the E sub A, or activation energy. But the difference between these is delta H for the reaction. And delta H here, because it's exothermic, should give you a negative number. So you actually take the amount of energy in the products and you subtract the amount of energy from the reactants, which when you subtract a small number from a big number from a small number, you get a negative value. But that's not what Hess's law says. That's just one scenario. To see what Hess's law says is maybe we could cause this reaction to take place in not just all at once where they slam into each other and break apart into products, but maybe it could occur in multiple steps. So for example, here's the aluminum and iron 3 oxide. It's starting in the same place, but maybe it requires some energy and it forms some kind of intermediate product. And maybe that forms some energy and forms yet another intermediate product. And then maybe there's yet another step and we finally get the reactant. While there may have been, say, 3 different steps here, the key thing is that the difference between the products and the reactants, this delta H for the reaction, is the same. And so if you're staring at that and going, Mrs. May, those don't look like the same magnitude. They are supposed to be. So imagine, ooh, let's make it more realistic here. How about that? There we go. Ooh, iron plus aluminum oxide. And now we can make it actually look like it's the same because it is the same. And that's what Hess's law says. It basically says, it doesn't matter how you get there, one step, many steps, the difference in energy between those two from reactants to products will be the same. So we can utilize that. So let's say that this, I'm going to rewrite the reaction up here just so it's on the screen again. let's say we know that this reaction actually takes place in 2 steps, or that there's 2 pieces of information that could be possible steps for this reaction. And so let's say that there's this piece of information about Fe2O3 that we know, and this is being provided to you, given information, that if you take some iron and some oxygen, you can produce an Fe2O3 molecule. Well, ionic compound, I guess, formula unit. And the heat for that specific reaction is negative 824.2 kilojoules per mole. And perhaps we're also given some information about Al2O3, that 2 aluminums and 3/2 of an oxygen react to produce Al2O3. And we know that the heat for that particular reaction is negative 1675.7 kilojoules per mole. These could be 2 different steps by which this reaction takes place. And if we want to use that and to use these values to figure out what is delta H for this reaction, then we need to manipulate the steps to get them to add together to equal this, what we're interested in. So I take a look at this very first one here, and I notice that I need iron as a product. I need Fe2O3 as a reactant. So I am going to take this reaction and I am going to flip it over. I'm going to reverse it. Fe2O3, making it exactly backwards, to 2 iron plus 3/2 of an oxygen. Now before, in this direction, it was exothermic. So if I reverse the reaction, now delta H for this is going to be endothermic. It's going to be exactly backwards. The other thing is I need, when I look at my chemical reaction, I need 1 mole of Fe2O3 and I need 2 moles of iron. And so sometimes I will find, oh, I need to multiply this by the number of moles I'm interested in. Well, I don't want to change it. I'm going to multiply it by 1. When I do that, I'm also going to multiply this by 1 mole. I want 1 mole of this reaction, essentially. Notice moles will cancel. Now I take a look at this and I compare it up here to my original, and I want Al2O3 as a product, and I have it. And I want aluminum, whoa, sorry about that. And I want aluminum as a reactant, and I have it. So I'm just going to rewrite this reaction down here. 2Al plus 3/2 of an O2 yields Al2O3. And I don't have to change this delta H because I didn't flip it around or anything like that. And I need 2 of these, not 4 or 6 or anything like that, and I need 1 of these, so it's good. I only need 1 of those, so I'm going to multiply this by 1 mole. If I needed to double it to help it match the equation, I would have multiplied it by 2 and multiplied it by 2 moles. If I now try to add these 2 reactions together, anything on the right side of the arrow of one and left side of the arrow of another, I can cancel, like the 3/2 oxygens. Cancel. And I can drop anything down on the left side of the arrow down here, so I get Fe2O3 plus 2Al yields 2Fe plus Al2O3. And then I can do the same thing here. Now the moles cancel, so my unit will be kilojoules. And I simply add these 2 together and I get negative 851.5 kilojoules. All right. I've done the work, but now I need to actually write it. Well, there's kind of 2 ways to write this. One is I've got the actual balanced equation. I'm just rewriting it for a moment here, sorry. And to that balanced equation, I attach delta H of the reaction is negative 851.5 kilojoules. Now remember, I said it's often kilojoules per amount of something for delta H of the reaction. So another way to write that, why is that not working? Go away. Or I could write this by interpreting this number in context of the chemical equation. So I could interpret as delta H for that reaction is negative 851.5 kilojoules per 1 mole of Al2O3. Well, how do I know that? Because in my balanced equation, I have 1 mole of Al2O3. So if I knew, for example, how many grams of Al2O3 were produced, and I knew how much energy I get per mole of Al2O3, I could use that to figure how much energy I would get. Or I could interpret it as delta H of the reaction is negative 851.5 kilojoules per 1 mole of Fe2O3. Well, why? Because in my balanced equation, I have 1 mole of Fe2O3, and that's what I got there. Or, I'm just trying to let you see there's a lot of ways to interpret this, or delta H for the reaction is negative 851.5, kilojoules divided by 2 moles of iron. Again, why? Because in my balanced equation, I have 2 moles of iron, and so this becomes 2 moles of iron. But I probably wouldn't leave it like that because I would divide it out. So if I take that and I divide it, I'm doing it in my calculator, but my calculator was not cleared, sorry. I would end up getting 425.8, say, kilojoules per mole, per 1 mole of iron. And so that might be helpful, and it's negative, sorry. It's helpful because if you know how many moles of iron or how many grams of iron are produced, you can also figure out how much energy was also produced. So that's sort of a helpful thing to do. Now, I want you to notice, going back to this, I had said that some of this was given to you. So sometimes, and you'll see in some of the blues problems, you're given steps of a reaction, you're given the overall reaction, and you need to manipulate the steps to add up to the original equation and then add up your manipulated energies. So that's one way that we could find delta H for a reaction. Another way that we could find delta H for the reaction, I sort of call this, I'll call this the long way. You don't really necessarily have a choice. It depends on what you're given. But sometimes you can do it via the short way to do kind of Hess's law. And the reason we call it Hess's law is because what we just computed was energy, assuming this took place in 2 steps. Did it? We don't know. But it doesn't matter because Hess's law tells us we get the same energy. Hess's law short uses an equation, delta H of the reaction is equal to, wow, that's a bad epsilon there, the sum of the heats of formation of the products, that's a mathematical sign, minus the sum of the heats of formation of the reactants. Heats of formation. Well, this is where you look at a table in your book, which I have conveniently taken a photo of over here. So there's this table in your book, table 8.3 in your chapter, and it's a standard enthalpy of formation at 25 degrees, and it gives all these different compounds. So what that means, in enthalpy of formation, if I take this silver bromide, and it says it's negative 100.4 kilojoules per mole, that's what it says up in the top of the table. What that literally means is if I were to take, start again. This is the energy required to make 1 mole of the compound from its elements. So that means for silver bromide, I would be making 1 mole of silver bromide from silver and bromine. Those are the elements. Except to balance it, I would need half a bromine because it has to be, according to the definition, making 1 mole of the compound. And so that means this is called delta H sub F. delta H of formation, it's to form 1 mole of the compound, is negative 100.4 kilojoules per mole. So literally kilojoules per mole of silver bromide produced. So this is an exothermic reaction. And in fact, if you look at most of these numbers, most of them are negative. Not all. Here's a grouping here that are positive. Oops, maybe just 2 of those. But most of them are negative in these heats of formation. So that is something that happens. So another way that we can do this is we could use this heat of formation table to figure it out. Now, one thing I want you to notice is that nowhere on this table are there any elements. Take a look. They're all compounds. If I go back to what the definition for delta H of formation is, it's to make 1 mole of a compound. So it has to be a compound. It can't be an element. What that means is that the delta H of formation for any element is always 0. Always. Some of you are going to take the test and try to look for an element and then come up to me and say, where is it? It's not there, Mrs. May. And incidentally, you don't have to memorize this chart. This would be provided to you, or the numbers would be provided to you. So if I go back to this short method, and again, I'm rewriting the equation just so I have it on the screen. What I need is I take the sum of the heats of formation of the products, and then I subtract the sum of the heats of formation of the reactants. I forgot that too. But I do have to consider how many moles of each I am making. So, if I want the heat of reaction, I'm going to start with this side here. That's going to be 0. I'm going to write the whole thing out. 2 moles of iron times, oh, it's an element, 0 kilojoules per mole. Are you going to have to write this all the time? No, I'm just trying to emphasize this. Plus I need 1 mole of Al2O3 times its heat of formation. So, ooh, let's scroll up. There it is, somewhere up here. Al2O3, I know it's hard to read. Oh, negative 1675.7. All right, getting dizzy yet? Negative 1675.7 kilojoules per mole. And that takes care of my reactants. Now I'm going to do the same thing, but I'm going to subtract for my reactants. So I'm going to subtract, I have 2 moles of aluminum, but aluminum's an element, so 0 kilojoules per mole. Plus I have 1 mole of Fe2O3 times, ooh, let's scroll, yay, somewhere up here. Fe2O3, it's hard to read, negative 824.2 kilojoules per mole. Negative 824.2 kilojoules per mole. Super, great. So now I've accounted for all of that, and when I do that and I plug it into my calculator, I get negative 851.5 kilojoules, because all the moles canceled out throughout, which then I can once again interpret in the very same way. I can say, attach it to the reaction and say delta H for the reaction is negative 851.5 kilojoules. Or I could be more specific and say, hey, yeah, it's negative 851.5 kilojoules per, go back to my balanced equation, 2 moles of aluminum, or 1 mole of Fe2O3, or whatever the case may be. You could interpret it just in the very same way that we did before. So, given the choice, certainly just looking at the table and using the short method and taking the sum of the heats of formation of the products minus reactants can be a very quick and simple way. But again, sometimes you're not given that. What you're given are steps of the reaction, in which case you need to be able to manipulate them like we did before. All right, that wraps that up. I'll see you guys in class.